You bumped into the ceiling, which now has to be washed and sterilized, so you get nothing. You lose. Good day, sir.
So sometimes there are a few things that we teach the intro class because it makes things a lot simpler, or we need to be able to all agree, but they may or may not actually be true. For example, the claim that 30 is this magic number that just fixes everything. And I've seen even official research that says, well, we had more than 30 data points, so everything works just fine. No, 30 was just an arbitrary number. There's some story behind it, but the point is, having more than 30 doesn't magically mean everything is fixed. Or in other cases, expected values of 5, or for proportions, that 15 number. Those were numbers we used in the intro course so that we all would agree. But in real life, you would look at the distribution, does it look normal? As it turns out, a lot of times, the normality assumption is fairly robust, meaning 8 to 12 actually gets you pretty good results. You don't ever get perfect results until n is at infinity, unless you know that it's normal beforehand, which it never is. So what do we really do? We take a look at the distribution, we try to say, okay, it seems like we're going to be getting reasonable answers out of this, and so we move on. But 30 is not some magic number that has any great significance. Another example, the idea that if your sample size is too small, and we already talked about how 30 isn't that magic number, that you just can't do the question. That's not true. There's always some other method. For example, resampling, bootstrapping, some parametric tests, likelihood ratio tests. There are several different ways to handle problems where the sample size is really small. If your sample size is really small, it's possible that it will be very hard to reject your null hypothesis because you don't have enough data to really show whether the null could be true or not. But that doesn't mean that you just say, cannot do. There would be a lot of science that would be thrown out the window if people just said, well, we don't have enough data, there's nothing we can do. Yeah, there is. There's always something. In this class, we will learn a few things, but you would need to take higher level stat courses to talk about a lot of those things. Number 3. The difference between Z and t-tests is whether you know sigma or not. And there's nothing mathematically wrong here. It's simply practical that if you're trying to test a mean, how are you going to know that standard deviation? If sigma was known, then you would probably also know the mean. So real life, these Z-tests don't really work. And I know what you're going to say. Well, at least for proportions, you're supposed to use the Z. Actually, not really. If you recall, when you have lots of data, those proportion histograms start to look like bell curves, but they weren't really. That was a little bit of a cheat, and it only worked for really large sample sizes, which is why we came up with this rule. But there's a different method called Fisher's exact test, which could be used and is better. It doesn't use the, well, it's approximately kind of close rule. So in the future, 15, 20 years, we might see stat classes where they don't ever use Z because either it's unrealistic or there's a better method out there. Why did we do it in the intro class? Because there's 80 years of tradition of people using Z, especially before computers. Z was a big deal because it was a lot easier. T-tables are difficult to use. And Fisher's exact test requires, 1 million calculations? Completely unrealistic, unless you have a computer, in which case it's easy. So those Z-tests are not common, and you're not going to see us really talk about them in this class. Also, we got a little simplified on our degrees of freedom. The two-sample independent t-test, we said the degrees of freedom are n-1. That's what's called hyperconservative, meaning that it's giving us the smallest degrees of freedom we could possibly use. That gives the null hypothesis a better chance of being failed to reject, because reject is when you can really show something. There were reasons why this was what we chose to be simple, but if you wanted to do the best test you could, we should have used what's called Satterthwaite degrees of freedom. The reason we didn't is because the Satterthwaite degrees of freedom are pretty nasty ugly, and it would have taken a lot of time on something that really wasn't that big of a deal for the intro course. So instead we just glossed over it with the simplified degrees of freedom. Good news is, from now on, the computer is going to do the calculation for us, and it will have the right degrees of freedom, meaning it will give us the right p-value. So we don't need to spend time worrying about this. So what's the important takeaways? 30 isn't magical, but we can always try to do the best we can, and that's not likely to be Z, and the computer will help us. Let's go ahead.